So throughout this course, we have been looking at different types of functions. So far in this course, we have looked at a linear function, which we represented with that slope-intercept form mainly. We did look at a couple of other forms of a linear function as well. And we looked at quadratics. Again, we had a couple of other forms with this, but I'm going to put the standard form, ax squared plus bx plus c. And what we've done is we've just gone through and discovered some things about how certain things in life follow a linear pattern, meaning they have a beginning amount and a change or moving amount, meaning you start at a point and then you go up by the same amount over and over. That is a linear function. There are things in life that do that. There are things that follow that pattern of having a beginning amount and a constant rate of change. We also, like I said, looked at quadratics, and we figured out that quadratics have this extra term here, this ax squared, meaning it's going to change the way my graph looks. My graph is no longer going to be linear because it's not just the mx plus b, it also has this x squared term. And so this x squared term causes this shape on the graph of a parabola. We talked about the important points on a parabola, like the vertex. How if the parabola opens down, you're going to have some other important points called the intercepts of that parabola. And we looked at things in life that followed this pattern. We looked specifically at things like revenue and area. When you're looking at a square unit of area and you're trying to maximize the area that you can have in a dog pen, or you're trying to find the exact amount of area that you need or the exact dimensions on a fence to reach a certain amount. We also looked at, like Rex said, revenue, where you are, owning a business, you raise the price, you're going to lose sales. You lower the price, you're going to gain sales. And so that gives me the ability to have this graph here that gives me a maximum or minimum value, that's vertex that we talked about. And so we looked at some real life situations that involve the quadratics. Today, we're going to be taking a look at a new function. This new function is going to be exponential. This final function of this course deals with things that follow a certain type of pattern also. And you've probably heard people talk about exponential functions before. So in the middle of 2020, we are experiencing a pandemic. And we are experiencing the coronavirus pandemic. And so what you notice about something like a virus and things spreading virally, if you talk about that, when you talk about a video that's viral, is, on day 0, when it starts, you might have one person that has the virus or one person that's watched the video. On day 1, that person has told a couple of other people, and now 2 people have watched it. On day 2, those people tell a couple people, and so now 4 people. Day 3, those people tell a couple people, so day has been 8 people. And so it keeps doubling as we go up. Sorry, guys. Up each day, we are doubling the amount. And what that causes is, on a graph, you will see that it starts at 1, but then it doubles to 2, and then it doubles to 4, and then it doubles to 8, doubles to 16. And it causes this graph to have what we have in an exponential function, a ramp sort of shape. And that's what I like to tell my students to compare an exponential graph to, is a ramp. Now we're going to get into the details of graphing in another video. Today what we're going to learn is how do you write an exponential function like this. And so the way that we're going to do that is we're going to just look at the 2 different types of exponential functions, exponential growth and exponential decay. Specifically, exponential growth occurs when a quantity increases by the same percent in each unit of time. We looked at an example just now of the doubling of a virus, and if that's happening, that's gaining 100%, not the same amount. This is not linear, so it's gaining 100% of what it had the day before. I go from 1 to 2, 2 to 4, because I gained 2. I gain 4, I gain 8, and that's 100% growth. That is not the same amount every day, it's the same percent every day. So when you have something that grows by the same percent, it is called exponential growth. The basic idea behind setting up an exponential equation is you have the initial amount out in front. That is not the same like we saw with the plus a y-intercept in linear and quadratic, so that's different. Your initial amount is multiplied in front. And you have a 1 plus the rate of growth inside of parentheses. And then you have t, or the time period. Yes, you can use x there. In fact, a lot of times in textbooks, you'll also see it written like this: a times b to the x power. The a being the initial amount, the b being the 1 plus r, the growth factor is what we call that, and x being the time. It's okay to have either one of these, because when you are dealing with exponential growth, when you talk about something growing by percentage, you can write it like this with kind of every little detail listed out for you, or you can go through and write it as 1 plus r already added together here and use x instead of t. That's not any different. So let me go back to that example we were just talking about. The beginning amount, we had one person with the virus, right? And then we were growing every day by 100%. So the rate of growth is 100%. So the tricky part with these problems is when you talk about 100%, you have to move your decimal place 2 places to actually put in your rate. And growth rate is 100%, but when you plug it actually into the function, you use a decimal, not a percent. And I know that's kind of weird, so you got to make sure you do 100% and move your decimal place. And you do that with any percentage when you're talking about growth. Then it's raised to the t, or the x if you want to use x. But notice what happens here. I start with 1, my beginning amount. 1 plus 1 is 2 raised to the t. What did we say was happening every time? We said it was doubling every single time. So with exponential growth, all you have to be able to do is you have to be able to find your rate of growth. Sometimes that's given to you. We're going to talk about some things in the real world for that in a second. And then you plug it in here. Your beginning amount is in front and your time period is here. Now we could then use this function to figure out, okay, after 30 days, how many are going to be infected? So we go to Desmos and we say, all right, I've got my function, and my function is a beginning amount of 1. I have 2 in parentheses because it's doubling every day. And then I'm going to raise this to the 30th power, 30 days. There would be 1.07 raised times 10, to the 9th power. I'd have to move my decimal place over 9 places. And so what you're talking about is 1 billion people. Now, obviously, that tells me that the rate, if I'm talking about the coronavirus, or the rate of a movie going out on YouTube, or some kind of little video on YouTube, I don't think my videos are going to get that famous. Do you? Probably not. But that's going to be a gigantic number with, basically essentially 9 zeros. So you're talking about 1 billion, and that's going to be a very quick growth. When things double, that's very quick growth. That's why, things like bacterial growth is kind of scary at times, because that can spread so quickly. We're going to look at this also in reference to things like a bank account too. Bank accounts grow by a percentage rate. So the thing that I'm going to remind you of real quick again is that in that percentage rate, make sure that you change it to a decimal before you plug it into your function. If you don't, you're going to accidentally plug in something that's really, really crazy, and you're going to get some really, really wild amounts. So we have our beginning amount, we have our 1 plus our rate, and we have our time. So let's take a look at maybe a more real-world example of that. Let's take a look at exponential growth for something like a bank account. This example says you deposit $500 into an account that pays 8% annual interest compounded yearly. Compounded yearly is a fancy way of saying the interest is added every year. We're going to write the function. So again, that's what we're practicing today, is writing the function. So I'm going to use that knowledge of exponential growth being that beginning amount, 1 plus the rate, raised to the time. So the beginning amount here is $500. That's what I deposit at the beginning. The 8% is 1 plus and I need to change this to a decimal by moving my decimal place 2 places, 0.08. That's where you got to be careful, because if you only accidentally move it one place, you got 80%, not 8. Now, yes, I realize, and I'll be realistic here, 8% is going to be something like an investment account, maybe a little risky, not a normal bank account. Okay, so when you start doing your little bank account activity for this module, you'll notice that you'll see some things that ask you to do some research about some percentages in bank accounts. Now, there are good accounts out there, don't get me wrong. There are other things like savings deposits and credits, some certain types of credit accounts out there that give you, like a certificate of deposit, and those types of things, credit unions out there that you can use. And this is raised to the t power. This is the function. Now, you can simplify it to 1.08 if you want to. You don't have to, because the calculator can do it for you if you just plug it in. But that also helps me out, because 108% is what I have at the end of each year. In other words, in my bank account, at the end of every year, I'm going to have 108% of what I had the year before. And so that's why that growth has that 1 plus the rate, not just the rate. And so that's important to understand. You have what you deposited plus the 8% of what you deposited. So it's 108%. Then you can use this function, like this particular one says, what is the account balance after 6 years? You can now use your function to plug in a number, just like we've done with linear, just like we've done with quadratic. And we can just type in that number and raise this thing to the 6th power. So we raise it to the 6th power, and that tells me $793.44. So $793.44. So that right there tells me that that's how much money I would have in my account after 6 years if I just left it there. Now, the beauty of this is understanding that exponential growth, that graph that we talked about, has that kind of ramp shape. So this is going to be a good thing for you to remember when you get to your quiz and your exam. If you understand the fact that it makes this little ramp shape because it's jumping up so quickly, you can understand that in a bank account, it's important for me to wait as long as I can, because that bank account is going to follow that same pattern. So the longer I can wait, the more money I could have in my bank account. We're also going to look at something here before the end of this video of a neat little thing that you can do and show what happens if you deposit more than once. So exponential functions that we do in this course only allow us to talk about one deposit. There are some higher levels of math where you can get into more than one deposit. So let's look at another example of that. You have a savings certificate of $1,000. It pays 6.5% annual interest compounded yearly. What is the balance when the certificate matures after 5 years? First, we're going to write our function. Our beginning amount goes out in front. We do 1 plus the rate, so we need to move this decimal place 2 places, so 0.065, and then we raise that to the t, the time. Now, I know, again, some of you may go ahead and you think, oh, well, Ms. Harrison, can I just go ahead and plug in the 5 years? Yes, if that's the only thing you're looking for, 5 years, and that's it. But some people want to know a little bit more. Some people want to know, well, how much would I have after 5 years? How much would I have after 10 years? How much would I have after 20 years? Whatever. It gives me the ability to keep going there if I know that this is a function with x in there. So I have $1,000, and I have 1.065 because 6.5% interest, and then I raise that to the 5th power. So $1,370.09 when you round it. Again, that's pretty good, and it's really important to understand, guys, you didn't do anything for that money. You just leave your money there. And that's hard because that takes some patience. Now, granted, again, 6.5%, 8%, those are pretty high interest rates. If in real life, you may be talking about something that's a little bit lower, but you still are not doing anything for that money except leaving it there. You're just being patient. That's the key. And patience is the key to understanding that an exponential function goes up and jumps up quickly. That can be a bad thing, again, when we think about viral spread. So when we talk about these exponential functions, anything that goes up by a percentage is going to be called exponential growth. And that can be population, that can be bank accounts, which is the one that we use the most because it's the most fun to look at, but it can also be things like the viruses that we see out in the world. Exponential decay is the opposite of that. Exponential decay occurs when a quantity decreases by the same percent in each unit of time. Because I'm a sports guy and I love basketball in particular, I always think of the NCAA tournament. On the first weekend of the tournament, on day 0, there's 64 teams. Now, I know they've added a couple of extra teams called play-in games, but we're going to stick with just 64 to keep it simple there. After the first day of the tournament, there's only 32 teams left. After the second day, there's only 16. After the third day, there's only 8. The Elite 8, the Sweet 16, right? After the fourth day, there's 4. Fifth day of the tournament, there's 2, and then after the 6th day, there's only 1. Only 1 champion left. But look at what's happened to those numbers. It's kind of just the reverse of what we saw before. This is going to start up here and then come down this way. But it's still that kind of ramp shape that we talked about. It's just decaying or decreasing by a percentage every time. So when we talk about exponential decay, we're talking about things that decrease by the same percent. Notice the only difference in that function is 1 minus r. What that means for me is when I actually subtract that, when I think about that a times b to the x, is that this b value right here is going to be bigger than 1 when it's growth and less than 1 when it's decay, because that's going to be a bigger percentage there when it's growth, like a bank account, and less than that when it's decay. Prime example, a really good example of an exponential decay function is something like a car value. So let me get to that example over here. You bought a used car for $18,000. The car depreciates, and you've probably heard this term, at the rate of 12% per year. This is what we're talking about, things that decrease by a percentage. So when we talk about that, that is going to be y equals 18,000, my beginning amount, 1 minus 0.12. I got to move my decimal place 2 places, remember, raised to the t. Now look at what happens there. If you do 1 minus 0.12, you're going to get 0.88, because that is going to be 88%. What that means is if you're subtracting 12% every year your car is only worth 88% of what it used to be the year before. And so that is what creates this decay function. So the estimating the value of your car in 8 years is the same thing that we did with the bank accounts. You just plug in your beginning amount into the calculator. Instead of a number that's bigger than 1, we have a number that's smaller than 1 because it's decreasing. And then we raise that to the 8th power, $6,473.42. Oh goodness, I forgot. 42? Yeah, 42 cents. Notice that the value of your car after 8 years is basically a third of what it used to be. Now, this is the importance of understanding that you don't have to buy a new car every time because that value goes down quickly. Let somebody else take the depreciation on that value, and you buy just a nice used car a couple years later, and you will be able to hold your value longer. Especially if you're one of those people that likes to kind of trade cars every once in a while. Don't buy a brand new one. If you buy a brand new one, you're basically taking, when you drive it off the lot, you're taking a couple $1,000s and just chunking it out your window, essentially. And that's just not real smart. So we have these exponential growth and decay functions. They're actually they're pretty quick to write. So when you're writing an exponential growth or decay function, you're just going through and you are having the adding a percentage or subtracting a percentage. I do want to make sure you understand that, like I said, the number inside the parentheses for exponential growth is going to be bigger than 1, and the number inside the parentheses for exponential decay is going to be less than 1. The only time that's going to be a little weird is if you had a negative in front of your exponent at the top. That's going to take that function and actually would kind of flip it, and so it's going to make it flip around to the opposite. I'll show you what I mean by that in the graphing video on the next one. So this is our exponential growth and decay. I'm not going to spend a lot of time on this because most people do pretty well with this. Let's do one more decay before we move on. Let's say we buy a computer for $1,800 and it depreciates at 29% per year. We take our beginning amount of $1,800, 1 minus 0.29 raised to the t. Or, in other words, 1,800 times 0.71 raised to the t power. So now, if we want to find the value after 2 years, just like we did before, we type in our beginning amount, and then we do 0.71, and we raise it to the second power for 2 years, $907.38. So notice, after 2 years, almost half the value is gone here, because what you're seeing is on an exponential function that is decaying. If it's decaying by a pretty high percentage, your value is going to go down really quickly. So these functions can be used, like I said, big thing is bank accounts. You can also have things like your car value when you're talking about the decay side of things. This is the same concept that people use when they're trying to figure out, and I always use this example in class, and like radioactive decay when it comes to radiation treatment for cancer patients. When you look at radioactive decay when it comes to dating rocks in the geological time sequence. I do want to make just a little warning there. You need to be careful. I'm not trying to sway you one way or the other. Just realize that those numbers, when you see an age for a rock, is a calculated number based off of exponential equations. There's not a little tag on the rock that says a certain age for the rock. It doesn't say, hey, I'm 2 million years old. It's a calculated number based off of assumptions that are made about how things decay. So you do need to be careful with that. When we talk about exponential growth and decay, it's a calculated function, just like calculating the value of this computer, or calculating the value of the car, or calculating the value of my bank account, whatever it may be. What we want to do is we want to be able to use these values. Guys, when you get out of college, start a bank account immediately. Start a savings account. It's one thing that I regret about not doing when I started. I got myself into debt really quickly instead of starting a bank account and having this money just earning interest as it sits there. Don't buy a brand new car. Listen to Mr. Harrison. Don't buy a brand new car, because if you buy a brand new car, it depreciates, and it depreciates immediately when you drive it off the lot really quickly. So buy used cars, and you can save yourself some value, and you can make the leverage of an exponential equation work for you and help you, actually. So what we're going to do, last thing we're going to do here, let me do two things. I'm going to do a little fun thing to end to. The last thing that we're going to look at as far as the math side of things is taking a table of values like this and plugging it into Desmos. I've made these as separate videos for the linear module and the quadratic module, mainly because I got through the video and I rushed through, and I forgot. Now, some of you are thinking, the video was an hour, Mr. Harrison. You didn't rush. But I was making sure I tried to cover the big important stuff, and I forgot to show you how to take a table of values and find the function for it in Desmos. So we've got these years: 1960, 100,000 black rhinos; 1980, 15; 1991, 3.5; 1992, 2.4. My suggestion here is to make this right here 1960, make this year 0, and then this will be 20 years later. This will be 31 years later, and this will be 32. And that'll make it a little bit easier when we go to plug these into the calculator. So on Desmos, and you can again watch the linear ones and the quadratic ones again as well. I made a video for those as well. We go up to this little plus sign up here, and I had you do this in the very first practice with Desmos. We type in a table. So we go down to the table, and we type in our values. 0, we said, for 1960, 20 for 1980, 31 for 1991, and 32 for 1992. And then we type in our values for population. We got 100,000, we had 15,000, and then the other two values, sorry, I'll have to go back here, 3.5 and 2.4, or 3,500 and 2,400. And that's my black rhino population. When you do that, you have these X1 and Y1, these values that you plugged in. You can't see them. So if you go to this little plus sign, zoom fit is what it says. This little plus sign down here will zoom in on those, and you can see, hopefully, that this graph kind of goes down like this and it starts to kind of level here at the bottom. That is that ramp shape we talked about. So what I can do is I can go to the next little spot in Desmos and I can tell it to find the exponential equation. The one thing you do have to do is you have to type in y1 so it knows that it's talking about these y values. And then you have to hit the little squiggly thing that is up to the left-hand side, probably under your escape button right beside number 1. Hit shift and that little key to get this little squiggly. And what that's going to do is that's going to give me what we call a best fitting line or a best fitting curve. Or technically in mathematics we also call it a regression curve is what we call it. So I want to do an exponential function on this one because that's what this one is. So I do use the little a times b. I'm not going to do my 1 plus r, 1 minus r, even though I know it's 1 minus r. And then I'm going to raise that to the exponent. Remember, you can do that on the keyboard down here, or you can use that little rooftop looking key that's right above number 6 on your keyboard. You can raise it to the x1 power. And what I had to do with the x1 there is because that's the x's over here. And notice it gives me this graph all of a sudden real quickly that fits my points. It also tells me that a is 100.069, b is 0.905. So what that means is my equation here would be y equals 100.069, so I'm going to go 0.7 times 0.91 raised to the t power, or if you want to use x there, you can use x there. Notice what that means in reference to my population. That means my population is decreasing, it's decaying, and it's 0.91. That means my rate of decrease, because it's 1 minus the rate, would actually be about 9%, because 0.91 is be like subtracting 0.09. So 9% would be my decay rate here. So that actually means, over the years, the African black rhino population is decreasing 9% every year. And that could be a dangerous thing to think. You're losing that population. Obviously, hopefully, like we see down at the bottom of the graph, it's hopefully going to be leveling off a little bit here. But eventually, it's still getting closer and closer and closer to 0. That's the whole point of what this graph looks like. We're going to talk about that in more detail in the graphing video. So you can do this with any numbers in here. You could have a bunch of different numbers. Like, let me go back and I'll show you real quick. I know I'm taking more time, like I said it wouldn't, right? Let's say you do that little example we started earlier with the little coronavirus example, basically. You had 1 person, and then 2 people, and then 4 people, and then 8 people, and then 16, 32, 64. Notice that it gives me that exponential ramp like we talked about. And then right here, it does tell me that A is 1 and B is 2. That's the same thing that I figured out when I talked about it myself over here. A is 1 and B is 2. Again, typically we use this format right here when we're kind of looking at like the bank accounts and things like that, and we're having to write it ourselves. We use this format right here a lot when we are using the calculator to help us out. But both of them mean the same thing. Both of them have the beginning amount in front, the growth factor on the inside of the parentheses, and the exponent is the variable. Guys, that's the reason really these are called exponential functions, is because the variable is in the exponent compared to those linear and quadratic ones that we did. The variable actually is up in the exponent, not in the base like these. So the last thing I'm going to do is I'm going to show you a real quick little fun thing. I'm going to go to a little website, and you're going to see this website later in one of your activities. I'm going to go to daveramsey.com. Some of you have maybe heard of this guy. He's a big guy about staying out of debt. At the top of the page here, he's got these little free tools, and there is an investment calculator right there in the middle. So I'm going to hit this investment calculator, and I'm going to do my current age. I'm going to just say we're 20 years old. I'm just going to make up a number here. And I think we did an example a little while ago, 6.5% interest, I believe it was, and we left it in there for 5 years, I think it was. 25. We deposited $1,000, so that's how much have you saved for retirement. Now, I know this is looking at retirement, but guys, we're going to look at it like a savings account. Right now, we're going to assume that we deposit nothing. We don't put any extra money into it. Our percent return, like I said, was 6.5%. That's got the little percent symbol, so you don't have to actually change it to 0.065. You can tell it to calculate, and this was the value that we had a little while ago, 1382. It's slightly different on here because I know that there's a little bit slightly different multiplication that they're using in there. I believe their algorithm may be a little bit off in their particular example there. So, or maybe let's see, make sure I did the right number. Yeah, it was 5 years. Okay. So, what we're going to look at is, okay, what happens if I quit drinking coffee every morning or every day? Let's say I drink, coffee, let's say just once a week. I'd cut back on one Starbucks coffee a week. So, we're talking somewhere around $5 or so. If that's every week, that's around $20 extra every month. So if I deposit $20 extra every month, watch what happens to this money all of a sudden. Notice instead of just, 1,380, I've got 2,796 by just doing a couple extra bucks, $20 every month. And that jumps up really, really quickly there. So you're going to do this in a little activity, a little bank account activity, and you'll come back to this site. If you have any questions about this, it's really cool to see what happens if you leave that money in there. And if you left it for a really long time, let's say till you're 40 years old, you did this for 40 years, you kept saving because you listened to Mr. Harrison in math class. All of a sudden, you're looking at $13,000. Again, that ramp shape of that graph starts to come into play more the longer you wait. And again, yes, the smarter you are with your money and not drinking that coffee every week or whatever. If you start saving more, it gets even better. And I'm just going to do one more here. Let's say we save $100 a month instead of $20. All of a sudden, I'm talking $52,000 in savings in 20 years. Guys, you can make the exponential graph. You can make it work for you. You can make that math be something that's fun again instead of just, I got to learn this stupid stuff. So that's how we talk about exponential growth and decay. Remember, like I said, exponential growth, you're adding a percentage. Exponential decay, you are subtracting a percentage.